Okay, guys. If you're missing a workbook lab manual, I found one in the lab. Let me know if it's yours. Epoxide handout. We'll also be getting to alcohol. We have a purple sheet and then one that you printed out on your own. Let's also look at NMR. NMR packet, let's look at that to begin with. Everybody have a good weekend? Yeah. Lots of good studying? Yeah. Playing in the snow?
Yeah. You call that snow?
I do.
Yeah, that's totally
Shade. It looked like cinnamon.
No, that was totally
I sent out the answer key to this NMR warm-up page. Any questions about that? Questions about this page? How you doing, Nancy?
Good, how are you?
All right. Any questions about this NMR page? Okay. Let's look at NMR. Let's skip a couple of pages. We both left off, Thursday and Friday lab left off at the same place. Let's skip over a couple of pages from there. And let's look right here. This problem, it says problem 24, problem 25. Bruce is an old textbook we used to use. No problem, no problem. We'll have problems here to work. I raised the board up a little bit. I think that may help give us a little more room with the molding tire. I don't know if this is going to help or not. It's still this line, but it seems like it's not as much. Okay, let's see if we can come up with structure here. I know a number of you are looking at the problems in the workbook, comprehensive spec problems. This would not be comprehensive. This is just proton NMR. In this particular case, the formula is given, C9H12. Let's come up with structure. Structure of this compound. One great thing to start with, if you're giving formula, is to do degrees of unsaturation, because that's very powerful. How many DUS is in this formula? C9 would get how many H's of saturated? 20. It's missing 8. Divide that by 2. 4. Okay, so we got a compound that has 4 pi bonds, 4 rings, 2 pi bonds and 2 rings, etc., etc. It tells you some information about the compound. Need to be able to do that because it's very important. Okay, we got peaks and they've blown up 3 different peaks. I'm going to start right here. We got peaks in the 7 to 8 region. What region is this? Benzene aromatic region, 7 to 8 ppm. Okay, aromatic region. Integration. We have this integral line. We can measure from where it starts to where it ends. Boom, 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 boom. If we do this with the old fingers here, if that's 1, how many is that? 1. It's the same. So we can maybe go 1, 1, 1, 1, 1.5. But we got problems. You can't have a half a proton. Maybe this is 2, 2, 3. And if that's 2, how many is this?
4, 5.
Well, that's 2. If somebody said 4, that means it would be double this. What more than double? I want to say 5. Why am I going to say 5? Because those numbers have to add up to what? 12. And so I knew I had over here 7, so that should be 5, right? That's also why I know it's not 1, 1, 1.5, and 2.5, because that's only 6 protons. And I got 12. Your integration has to add up to how many H's you have. If you're given formula, you can make sure your integration numbers add up to that. If you're not given formula, well, you have to just kind of estimate until you get more information. Okay. Aromatic region. What's the most common aromatic ring? Benzene ring. Do you know any other aromatic rings at this point? No. Test 2, we will learn others. Okay? At this point, I'm going to highly recommend that when you hear hooves, you think horses. Alright? Ever heard that term?
Yeah.
Okay, when we hear hoof, we're not going to think like zebras or llamas. Most common would be horses. So I'm thinking horses, and here that's benzene ring. Alright? So I'm going to draw a benzene ring. There you go. Well, obviously there's more to it than that, because that's only C6. How many H's are on this benzene ring? Well, the one I drew, there's 6 on there, but how many are on there of the structure we're trying to come up with? 5. 5 aromatic H's. Okay? So maybe we can draw something like this. That is, each one of these carbons has an H. There's 5 H's. What's here? Something that's not an H. For example, it might be a chlorine. I mean, obviously no chlorine. But if it was, it'd be 5 H's. And then the other thing on there is a chlorine. Not 6, but 5 and something else. So this is just saying that there's 5 there. And then there's something else coming off. I don't know what it is yet. I'm going to say this is mono-substituted benzene ring. It's got 1 substituent. What if this number was 4 here? How many substituents would your ring have? 2. 2. I think you got the hang of it there. Now, that's it. Do we even need to look at this splitting? You don't need to. Because just the fact that we're going to go with benzene ring, and we know it has 5 H's, it's got to be this. Unless it's some crazy aromatic ring, but I told you, don't go there yet. All right, let's go down here. What is this here? How many H's is this signal for? 2. That's what the integration tells you. Okay? Now, these H's are most likely on carbons. Because if they were not, if it was on an O or N, we haven't really talked about this specifically, you wouldn't get the splitting. Splitting H's are on carbons typically. What is this signal here? It's not given for you. 2.4. It's been blown up right here, right? That's it. What is that? You want a triplet? Okay. Triplet 2H. What is this in terms of multiplicity? That's a multiple. They blew it up here. Multiplet 2H. And what is this one on the end? They blew it up here. Triplet 3H. Okay. The fact that this is 2H means it's a CH2. Now, it doesn't have to be. It could be 2 equivalent CHs that add up to 2 H's. But we're going to think who's or horses, right? What is next door to the CH2? What would make it a triplet, Larry? What would make a signal a triplet? It would have how many neighbors? It would have 2 neighbors. Because we know neighbors plus 1 gives you what your signal is going to be. So for it to be a triplet, we're going to have 2. That makes n plus 1, 3. That means the neighbors is what? Not a CH2. Do you agree? And then there's something here. Would this be a triplet?
No.
Well, there's nothing over here.
Yeah, yes it is.
Would that be a triplet?
Yes.
Yes, because 2 neighbors and plus, yeah. So what I'm saying is, this is what I'm putting together. It has to have a CH2 neighbor for it to be a triplet. Let's go over here. First off, there's 3 H's, so I'm going to say it's a CH3. What makes it a triplet? Neighbors. How many neighbors does it have? Would that be a triplet?
Yes.
Yes.
2 neighbors and plus 1 triplet. Would it be integrate for 3 H's?
Yes.
Yes. So I've got these fragments together. How many carbons do I have on the board? 6, 7, 8, 9, 10. But there's only 9 in the compound. What do you see?
The CH2 on top and the CH2 on the bottom is the same?
You're saying these are the same?
Yes.
And let's sort of put it together like CH2, CH2, CH3. That is, we still have the CH2, CH2, but we also have the CH2, CH3. Now, let's go back and check. Would this be a triplet 2H? First off, yeah, 2H. Would it be a triplet?
Yes.
Yes, it's next to 2, and plus 1 is 3, triplet. Would this be a triplet 3H?
Yes.
Next to 2, and plus 1 is 3, triplet. What would the middle guy be? I split on both sides. This would be a multiplet. How many H's?
12.
It gives 6, right? It has
2.
5.
There's 2 H's there.
2 H3.
It'd be that right there. Multiple 2H. Yep, the third signal. What we have here is just a plain old purple group. The way I put it together is the systematic way of putting it together and interpreting the peaks, building structures. So what do you think's coming off this benzene ring? It's just purple. And there's your compound right there, purple benzene. Christian, Kesha.
So, let's say if you had a dye-substituted benzene ring, does it matter where you put the substitute?
Yes, it would.
Are we learning that eventually, or?
Eventually, but not in this example.
Okay.
Yeah. But we actually did some of that in that where we predicted the number of peaks.
Okay.
Okay. Question.
When you have multiplets, do you not look at neighbors so much? Because in that multiplet it's 8, and so that would say 7.
Oh, we really don't need to do it. I mean, what else could it be? that's the last piece of the puzzle. It has to be the CH2. And usually your multiplates are going to have complex splitting, which we haven't covered that sheet yet. But it's, yeah, you don't really need to look at this. It's what, 1, 2, 3, 4, 5, 6, 7, 8. Well, it shouldn't be 8. It should be more than 8. Sometimes you don't, these little side peaks don't show up. Sometimes tall peaks in your multiplet can be on top of each other, like these two fingers, and it's not all separated. Theoretically, what you predict for a multiplet is different from what you often see. Okay. What else could the structure be? Why is the structure not... First off, how many DUS does our structure have? 4. 4, like it's supposed to. By the way, once you know there's a benzene ring, how many DUS are in the side chain?
None.
None. So don't go putting the alkene here, then you'd have 5 and you wouldn't match your formula. Why is it not isopropyl benzene?
The signals don't match. The integration is that one loses an H.
Well, what would the integration be here? You would have, what would this signal be?
The integration would be 3 for the 2 on the ends and 1 for the thing in the middle. It's 2 and 3.
Three.
So it would be a doublet.
Integration here would be 6H.
Add doublet.
Be doublet 6H. And this would be, what would this be?
Quartet?
Multiplet 1H. This is split by 6 neighbors. That's actually going to be a septet. This is split by 1 neighbor, doublet. Let's see, what is that? That's also a doublet. But this is the same exact doublet. So it's just going to be 1 doublet. But the integration will be for 6. It's the same signal, right? They're equivalent. They don't get 2 doublets. So that's why I didn't say doublet 6H again. The fact that there's 2 comes up in your integration. Now, all 6 do split this signal. Question. So that's only 2 signals. We have 3 signals.
Yeah, why is that one a multiplet, not a quartet? Because they're like identical CHs.
Yeah, identical?
Yeah, so why isn't it like 3?
No, how many neighbors within 3 signal bonds?
6.
6. 6 plus 1 is 7. I mean, just because they're on different carbons doesn't make them not within 3 signal bonds. Okay. So there was one there. What's on the next page? The next page, we have an IR and a proton NMR. And you will see there's no formula given. Let's go ahead and work this one real quick, and then I'll let you work the rest of them. You also need to be looking ahead, carbon NMR, etc. Maybe each day we'll do a little bit. Let's see what we got here. Quick look at the IR. Do you see anything? First off, well, there's no formula. We can't do DUS. This is a pretty strong peak here at about what? 1700. What do you say that is? Looks like a carbonyl.
Is that a ring structure there to the left of the carbonyl?
Like an aromatic signature?
Yeah.
Okay. How can we confirm aromatic in the proton NMR? Peaks at 7, 8? What do you want to show here? How many substituents on the ring? There's different signals here. We really don't have to interpret the splitting here because the integration, there's 5 H's here. That means there's 5 H's on the ring. Unless you had 2 different rings and one ring had 3 and one ring had 2. But let's start simple, like the horses, okay? Again, it looks like mono substituted. Does everybody understand why? Because there's 5 H's. If it was di-substituted, there'd only be 4 H's here. If it was hexa-substituted, there wouldn't be any signals here at all. That'd be wild and crazy, wouldn't it? Have an aromatic ring with no signals, because if it doesn't have any H's on it, then, well, okay. What do we got here? I'm giving you the integration. Well, that's a giveaway. Already telling you what the integration is. We didn't have to measure it, right? 2 and 3. But if you had to, you could say, hey, that's like 1.5 longer than that. So this is a CH2, and that's a CH3. Most likely. Oh, well, come on. This is like, okay, we don't have to do anything else. Just what else can it be? They're together, right?
Yeah, it should be still mono. According to the IRs.
Let's just see if this matches this ethyl.
Because you also have sp2 CHs.
I'm going to focus on the NMR because the NMR is the most powerful. I'm telling you, it's powerful. Yes, there's stuff up there. This right here is going to tell us what we need to know. Except for that guy right there, because we're not going to see that in the proton NMR. Because it has no protons.
I'm a little confused as to why you could lump all those first 5 carbon together even though they're not in the same peak.
Well, we wouldn't expect the same peaks, because what if this is chlorine? How many signals would you expect from chlorobenzene? 3. What you may want to ask is, why was the previous one only 1 peak? Well, it really wasn't. Theoretically, with propylbenzene, you would have expected 3 aromatic peaks. But a lot of times, the peaks are just not separated because the 3 are like this. They're just on top of each other. Theoretically, we expect 3, but in practice, you only get what looks like 1 because they're just so close to each other. These are spread out a little bit more for some reason. Does this fit the ethyl? What is this? A triplet?
There's a multiple.
I can't see it didn't expand.
It's got 4.
Is it a quartet? Quartet 2H. And what is that? Is that a triplet? Triplet 3H? Okay, let's look at this. What would you expect for the splitting here? Something 3H. What would that be? Two neighbors, and plus 1 is triplet 3H. What would you expect for here? Assuming nothing's here. Because there's something here, like a CH, we have another peak. There's no other peak. Quartet, 3 neighbors, n plus 1 is 4. Quartet, how many H?
2H.
Quartet 2H triplet. Is that what we got?
Yeah.
That's what we got. So boom, we confirmed this. That fits. Okay. Let's see. So my structure is just ethyl benzene. A benzene and an ethyl.
You need a ketone.
Oh, the ketone that we saw in the IR. Oh, which is most likely why the IR was given to you. Because again, you can't see ketone. Well, let's just put a ketone on the end.
Then that would take away the
Well, now it's no longer an ethyl. So where do you want to put the ketone?
Yeah, right after the
How about right there?
But then it takes the H.
Then it's no longer an ethyl. We got to have an ethyl. Where do you want to put the ketones?
Add another carbon.
Add another.
How about slip it in between? There's your mono substituted. Here's your ethyl. There's your carbonyl. Would the splitting still be
Yes.
the same?
Yes.
There's no neighbors over here. What would the carbonyl do to this signal? It's not going to change the splitting, but it would
So you say it could go upfield?
Shielded.
downfield.
Oh, yeah.
Look, see how this signal's a little downfield compared to the other one? What makes this downfield?
Resonance. Electron density.
Deshielding by the carbonyl. Okay? You look back at your tables. Peaks next to a carbonyl is going to say like 2 to 3, or maybe 2.5 to 3.5. Okay? Something's made this downfield. That's your structure. Does anybody have another structure you can put together that would match this? I mean, we could put several together. How about that? Of course, I just can't draw an aldehyde without drawing the H on there. How about that? What's about that? Well, I don't see a signal for the aldehyde, which would be where?
Downfield.
9 to 10, that's aldehyde region. Okay? Also, now my ring has got 4 H's on there. Right? Only 4. But the NMR said it has 5. So you can't do that. Okay, there's a couple other to work. At this point, you need to also be looking at the ones in the workbook, which are even more comprehensive. They include carbon NMR, they include mass spec. But we just did that without formula, right? I mean, do you think there's more carbons? You want to add some more here? Well, if you do, you should get signals for what you added, unless they don't have H's. Maybe there's 3 chlorines here. I didn't add any H's, there's no signals. But we've ruined our ethyl. There's no longer an ethyl. Think about it. We did that with no formula. Okay, let's look back at epoxides. Did you try your man did some synthesis? How about this guy here? You guys try these? Any questions about these? Stephanie, did you try one of these?
No, I don't have.
Let's go over here then. We did terbutylene. Let's look at polymerization of epoxides. Anybody heard of epoxy glues? Huh? How do they work? Do you have 2 different things? What do you combine them? And when you combine them, what happens? It sets. We call it setting. It sets, right? It polymerizes and it dries and it turns into a glue. Okay? Something like that. Epoxides are prone to polymerizing. Here's the simplest epoxide, ethylene oxide. Why is it called ethylene oxide, by the way? What is that called? Ethene, also commonly known as ethylene. If you add an oxygen to ethylene, what do you get? Ethylene oxide. That's where this basic name comes from. If you treat this with hydroxide, you can get a monomer, but you're also prone to getting a polymer. Okay? Anytime you do a epoxide reaction, you're prone to getting polymer if you don't do it right. First off, how do you get monomer? Well, hydroxide, aqueous, attacks it, opens it up. What does this give? Well, there's no H there. Here's the nucleophile. Nucleophile, carbon, carbon. We'll get an H here. It'd be, where can H come from if we get the monomer? Water, yeah. Solvent can supply proton to these here. And if we finish this up, you get that plus what? Hydroxide. So this is really adding water to this, and hydroxide is the catalyst. Okay? How would you get polymer?
With the hydroxide that comes from the water.
What if instead of this getting an H, it attacks here and opens that up? What would that give? It would give that. Nucleophile, carbon, carbon, OH. If it gets an H, but instead of picking up an H, what if it tagged here? What would that give? And we just made that bond there. Nucleophile, carbon, carbon, O. This could pick up an H, but what if instead of picking up an H, it attacks? Somebody stop it. Okay, do this another gazillion times. It just self-reacts over and over. How do we want to draw the structure? Could we draw this as sort of a repeating unit?
Yeah.
OH on the end. From there, what do we have?
Carbon,
Carbon, carbon,
Carbon, carbon, O. Carbon, carbon, O. Carbon, carbon, O. If we keep on going, it's going to be, after that, CH2, CH2O. CH2, CH2O. So that's kind of a repeating unit that goes on and on and on if we just do the structure out over and over and over. And that thing, which would be a gazillion miles long in terms of molecular size, would have a huge molecular weight, and it would be a solid. It turns out it has properties that makes it stick together very good and stick to other top things. I mean, the polymer chemistry and polymer industry is very practical.
So they function like hydrocarbon and you just kind of stack on top of each other?
I can't give you a quick answer to why the properties, what about the molecule leads to the properties that makes it stick. It's not really, it really doesn't become sticky, it just adheres. I don't know, I don't have, some of you people that use, anybody use epoxy glues? They just sort of harden. The hardening forms a bond somehow. I can't.
Looks like a pretty decent H bond in there.
Yeah, but it does have a lot of carbons also. Everything we talked about is sort of relative. Okay. Which is more important property, H bonding or carbons? Well, in the end, then you just properties.
Do you think it could bond, like, as far as the glue properties? Could it be like, if there's a little bit of moisture in the wood or something, that could cause it to bond? make it sticky?
Well, these are all questions that, again, I don't have a short answer for you.
There's better questions, how do we stop it from doing that? That's not what we want.
There we go, something okay. What if you wanted the monomer? We get into practical stuff we usually don't have time to talk about, okay? You get into chemical engineering, though, you're going to talk about more of these practical things. But here it is, we need to move on. But the question is, for example, do you want to have your epoxide in the flask and then add the hydroxide? Or maybe do you want to have the hydroxide in the flask and add in your epoxide?
Yeah, second.
Why the second? I think that might be right. Why the second, Keith?
Well, because there's less epoxide
Less epoxide.
and more water, so react water more readily.
So this is more prone to react with water than other epoxide. Yeah, you want to keep the concentration of the epoxide low throughout the course of the reaction, so it's more prone to taking an age. And so you can do what's called reverse addition. Usually you take your main organic compound in the flask and then you add your reagents. But instead maybe you put your hydroxide in there and you slowly drip in your reagent epoxide. And when this forms, for example, what if you could add one molecule at a time?
That'd be awesome.
That'd be cool, wouldn't it? And once this forms, there's no other epoxide around because you only added one of these. Then it could just protonate. Then you add the next one. Of course, we can't add one molecule at a time. At least not today that I know of. But you could say, okay, what's the next thing? Well, let's add a drop at a time instead of all at once. So rate of addition could be the way to control it. Lots of different polymers. It's the same ingredients. You just get a different outcome based on how fast you add one thing or what temperature you do it at. And polymer chemistry is a huge, wild field. Okay? I mean, it's like crazy. You can go work with 3M, develop new polymers all day, and try to make new applications. Make frying pans better and stuff. Make lots of money. Everybody wants a good frying pan that cleans easy. All right. There's a question over here. You can read about it next time you eat hamburger meat. Just think about things. Question down here: retrosynthetic arrow. That means this is a target compound, and asking you, well, what if you went back to this? How would you then come forward? Really, that's what it's asking. If I gave you this, could you give a synthesis of that? Well, the chemistry is taking place here, right? Everything else is the same. What you got to recognize is, first, epoxide is very powerful in giving in synthesis. What type of product do they give usually? Well, not usually, all the time. Nucleophile carbon-carbon OH. Do you see it? Nucleophile carbon-carbon OH? Epoxide. Okay. So we back this up to, if I had an epoxide, could I make that? Hopefully. Well, then you say, well, how do I make the epoxide? MCPBA reacting with what? Alkene. So you show your alkene, and then you say, well, how can I make the alkene? Eventually, you got to go back to what I asked you to go back to. Can you make an alkene from that? Okay. So do that one. Please work on the multi-step synthesis. We'll take a little bit of time. There's some interesting things here about epoxides. There's the puzzle. Synthesis of Prozac. Oh yeah, that's a good question here. Synthesis of Prozac, they start with this starting material. I know the type of alcohol this starting material is? What type of alcohol would you call that? Michael, you know that one?
It's an aliphatic.
How about Michael over here? Got two Michael. This is an allylic alcohol. It's discussed in your chapter. Okay. MCPBA would give the epoxide. Of course, it would give two enantiomers because this is chiral here. just use MCPBA. You can separate an antimer. In organic 1, we talked about using acid-base chemistry to separate an antimer by forming diastereomeric salts. There's other ways to do it. They separated out, got this enantiomer. Then they reacted this with something to give this product here. Question is, what nucleophile did they use here? And not the name of it, but what in terms of just the atom, or atoms. Molecular. What nucleophile was used here? Oxide, nucleophile, carbon-carbon OH. What nucleophile was used? Paige, you see nucleophile? Courtney? Byron, you got something? The nucleophile ends up on which carbon? Nucleophile, carbon, carbon, O. So which carbon? That carbon has a nucleophile? That one?
Yeah.
Nucleophile, carbon, carbon, OH. So what's new on this carbon? Well, here's that carbon. How many H's are on this carbon? One. How many there now? Two. So what's new on that carbon? An H. That's what's new. So if H is a nucleophile, it's in the form of what? H plus or H minus? H minus. H plus is not a nucleophile. If we had H minus, can you envision these electrons attacking here, picking this up, adding a new H to that carbon? And what would this pick up with workup? Gets an H with workup. Okay? They're reacting it with hydride. Now C, what is the reagent? DME is the solvent. Red owl. When you add H, is that a reduction or an oxidation? Reduction, yeah. Red owl is an aluminum reagent that has hydrogens. This supplies hydrogens. We'll see, it's kind of a slang name. It's reducing aluminum hydride. We'll see more reactions like that as we go forward using hydride. You'll also see some on the epoxide puzzle. What hydride sources do we know other than red owl?
NaH4, NaH.
NaH. NaH is really not good as a nucleophile.
BH4.
Sodium borhydride. There's another one with aluminum. Maybe on the epoxide puzzle, we'll see it going forward. Lithium aluminum hydride. Okay? Lithium aluminum hydride. The red owl is a variation of this, where it's aluminum. Hydride. What do they do next? They convert the OH to what? A mesylate, similar to tosylate, except they have the methyl on the end. Why? I'm thinking they're probably going to do a leaving group reaction. Have this be a leaving group? Lo and behold, they do. What do they react it with? Methylamine. These electrons kick off the mesylate. Then you lose an H to go neutral. See, they don't even show a base here, but I guarantee you they worked it up with base. Get rid of that proton. Then what did they do? They got the oxygen on the ring. This is a nucleophilic aromatic substitution. We'll do this chemistry during test 2. That's a test 2 reaction where we do aromatic chemistry. Okay, so there's use of an epoxide. A couple other things. Important to take time to just see the application. Antifungal drugs like Lamisil, how do they work? Well, they kill the fungus. How do they kill the fungus? They inhibit an enzyme called squalene epoxidase. What does that enzyme do? It converts squalene to this epoxide. One of these alkenes gets turned into an epoxide. Maybe that one on the end right there. Then they drew it in a kind of a unique conformer here. From there, reaction takes place where all these rings form. Now there may be a mechanism in the workbook that's sort of like this. I mean, the fungus uses enzymes to do it. You can probably do this in lab with like H+. Amazing reaction. Put this steroidal four-membered ring together, or four-ring system together. So, drugs can inhibit this conversion here. Eventually what you're inhibiting is the synthesis of progesterol, which is important for the fungus. Oh yeah, there it is on the next page. I just showed it for you using proton. Make sure that that reaction looks good to you. Another thing, you ever heard of polycyclic aromatic hydrocarbons, how they can be carcinogens, diesel fuel? What's known to happen is some of the double bonds of the rings can become epoxidated. And then what do we know about epoxides? They're very reactive, they're very electrophilic. Any nucleophile, strong or weak, tend to react with them. Your DNA has lots of nucleophiles, like amino groups. Those amino groups react with those epoxides and permanently modify your DNA that can cause cancer. So the epoxide is involved in the mechanism there. Of course, glutathione is a protecting agent in your body. We talked about glutathione in Organic 1. Sulfur has a good nucleophile. Sulfur is a good nucleophile. The glutathione can react, and it acts as a sacrificial nucleophile to protect you instead of your DNA. So a little bit of application. Then there's questions. These should have been in the workbook, but not. Those are workbook type questions. But the answer key is on the back. Okay, epoxide is very versatile, very reactive. Let's move on to alcohol oxidation. Anybody need a composition notebook to keep your questions written down here? Somebody over there raise your hand. If you come by, I'll give you one. Remember, we do have the green sheet, which is sort of our outline for the whole test 1. And we finished up the first page, except for the oxidation of the alcohol. Basically, we're going to do that now. Here's sort of a summary, but it's written in the other handouts too. After alcohol oxidation, we'll do alkene oxidation. Okay, there's also a handout that you printed on your own.
Our first test is 2 weeks from today, isn't it?
2 weeks from today? 2 weeks from today? Yes. Alcohol oxidation and alkene oxidation, those are our last topics. The important other topic that's out there is the NMR. Okay, you need to be working to get to the comprehensive NMR spectroscopy. Okay, alcohol oxidation, very important. Here's just an example. Estradiol has this alcohol up here. it is converted in the body by oxidation to estrone, which now has the ketone. Okay? So this is estrogen conversion. What's going on here in terms of formula? There's an H there. 2 H's are removed. Remove the H from there, remove the H from there, and now we can put in a pi bond. Okay? So you can say like minus 2H. It's a very generic listing of what's going on. When we lose H's, what do we call that in organic chemistry? Oxidation. Okay? The alcohol is being oxidized. Now we'll learn how to do this in the lab. Of course, the body usually uses some very sophisticated enzymes. If you look on the next page, it shows a lot of the steroidal synthesis, both sort of testosterone based and also estrogen based. Let's look at oxidation of alcohol here. What we see is primary and secondary alcohols can be oxidized. Tertiary alcohols cannot be. No reaction. Now, what we're doing here is we're essentially removing 2 H's. Okay? Removing 2 H's, putting in the pi bond. If you do that, what do you get? Now have pi bond to oxygen. Yeah? 1 H remaining. What is this functional group? Aldehyde. That's the same thing there. I just drew it with the oxygen up instead of down. Okay? O with brackets is a generic term for oxidation. Okay? And you can also say minus 2H or something. But when you oxidize a primary alcohol, you get an aldehyde. Now, do you have to memorize that? No. By the end of, when you get to, you'll know it by the end, once you learn it. But ultimately, if you remove 2 H's, that's what you get, and you step back and say, hey, it is an aldehyde. We'll learn that aldehydes are susceptible to further oxidation. It does require water, and you'll get a carboxylic acid. All right? This is not removing 2 H's. This we added an oxygen. That's another way to judge oxidation. When you add oxygen, that's an oxidation. It does require water. We'll learn about this. Also important is oxidation state. Okay, and let me end right here. Way to judge oxidation state in organic chemistry, usually carbon, is number of bonds to a more electronegative atom. How many bonds to a more electronegative atom does this carbon have? 1. How many now? 2. It's been oxidized. If you go this way, we say it's been reduced because we reduced the number of bonds to a more electronegative atom. How many bonds to a more electronegative atom there? 3. So it's been further oxidized. Okay? Now when you oxidize a secondary alcohol, of course if you lose the 2 H's you get this structure, right? And lo and behold, it's a ketone. You're just playing with it, right? All right, we'll pick up here running strong on Wednesday.